Our next topic will be a DC shunt motor speed control. So there's nothing but a speed control of a DC shunt motor we are going to discuss. So to control the speed of a DC shunt motor, before let us know the equation for the speed. So we know that the back EMF EB is given by 5P NZ by 60A. Using that equation, we can write the equation for N as EB into 60A divided by 5PZ, where 60 is a constant, A parallel path is a constant, P number of poles is a constant, and Z the number of conductors is a constant. So if N will be proportional to EB by 5. So your speed is directly proportional to the back EMF and inversely proportional to the flux. So if you consider the back EMF, so we know that a back EMF is given by V minus IARA. So this is the equation what we have. So N will be depend on the back EMF and the flux, which in turn your back EMF will depend on the IARA because V will be the fixed one. So from this it is clear that we can control the speed of the motor by using two methods. One is a flux control method, that is by varying the flux phi, and next one is armature resistance control method. By controlling the armature resistance or the current flowing through the armature, we can control the speed of the motor. So these two are the different methods what we have to control the speed of the motor. One is flux control method, another one will be the armature resistance control method. Now let us go with first method, field control method. So as we know that your EB is 5PNZ by 60A, so N is given by EB 60A by P5Z. So from this we can make out that N will be inversely proportional to 1 by 5. So actually your N will be proportional to EB by 5. Since we are discussing only about the flux control method, let us consider only with respect to flux. It is given by 1 by 5. So as we know that the speed is inversely proportional to the flux, correct? So here by varying the flux depending on the whatever the current flowing through the field winding, we can control the flux. So here you can observe we are adding an additional rheostat in series with the field winding, so which will add an additional resistance, so which will control the current flowing through the field winding. So by this method what we can do is whatever the current flowing through that we can control through the rheostat. If you kept at the minimum position, so the maximum current will flow through the winding. If the rheostat is kept at the maximum position, it will limit the current flowing through the field winding. So by this method we can control the current flowing through the field winding. So again, which your flux depends on the current. So as we can control this, we can control the flux. By controlling the flux, we can vary the speed. So as flux decreases, your speed increases, or your flux increases, speed will be decreased. So because it is inversely proportional. So if you consider as current increases, you can see here as the current increases, the flux increases. As flux increases, the speed has to be decreased. So that is what how we can control the speed of the motor by using a flux control method. Next one will be the armature resistance control method. So this is the another method how we can control the speed of the DC shunt motor. So if you compare with the previous case what we have discussed with the flux control method, we have connected a external resistance in series with the rheostat as field winding, but here what we are doing is, since it's an armature resistance control method, we are connecting an additional rheostat in series with the armature. So how we can control? So whatever the voltage available across the armature, by varying that we can vary the EMF. So as we know that your EB will be equal to V minus IA RA, right? Again we are inserting one more rheostat here, so your EB equation will become V minus IA into RA plus an additional rheostat what we are using. So when your rheostat value is at minimum position, the normal back EMF you are going to obtain. When you are going to increase the rheostat value, so obviously your drop across the armature resistance will increase. Because of that your back EMF decreases. So when back EMF decreases, as we know that speed is directly proportional to EB. So as current increases, your back EMF decreases. So as back EMF decreases, obviously speed also decreases. That's why we are going to get the plot like this. So these are the two methods by using which we can. Now let us see what are the advantages of a field control method or a flux control method and the armature control method or a rheostatic control method. So if you consider with the advantages of a flux control method, so it provides a relatively smooth and easy control. So we can control the speed of the motor by just varying the rheostat which is connected in series with the winding. By using that, easily we can control the speed of the motor. And the second advantage is the speed control above the rated speed is possible. So whatever the rated speed of the machine is given, so above that we can increase the speed of the motor by using this particular method. And the third one, as the field winding resistance is high, the field current will be very small. So if you consider with the field winding resistance, it will be very high. Because of that, the current flowing through the field winding or the field current will be very small. Hence, so the drop, that is I square R drop, will be very low. So as the resistance is more, the current decreases, so your I square R loss, that is copper loss, will decrease. So this will make the system more economical and the efficient one. So now if you observe the disadvantages, right, the speed control below the rated speed is not possible here. Only we can get the speed control above the rated speed or up to the rated speed. Below the rated speed, if you want to control, we cannot go with this particular method, as the flux can be increased only up to its rated value, and as the flux reduces, the speed increases, but the high speed will affect the commutation, making the motor operation unstable. So as we already discussed with the concept, right, when flux decreases, your speed will be increased. So but whenever we go with the high speed, right, it will affect the commutation and everything, so it will make the system more unstable. That is the main disadvantages of a flux control method. So now if you go with the advantages of a armature control method or the rheostatic control method, another name. So first one will be the easy and smooth speed control. Below the normal speed is possible. Here whatever the rated speed is there, below that we can control the speed. And in potential divider arrangement, rheostat can be used as a starter. So whatever the rheostat we are using here, so it can be used as a starter. That is the main advantages of a armature control method. If you go with the disadvantages, so as the entire armature current passes through the external resistance, then there will be tremendous power loss. So here, so whenever the current, armature current will pass through the entire current will pass through the external source, so because of that there will be a more I square R loss will be there. Next, as armature current is more than the field current, the rheostat requires large and the capacity of that should be very more. So if you compare with the field current, whatever the current we have going to flow through the armature, it is very high. That's why whatever the rheostat we are going to connect in series with the armature, it should have with the higher capacity. And one more disadvantage is the speed above the rated speed is not possible in this method. How we are controlling the speed above the rated speed in case of a flux control or field control method, right? Here we cannot control like that above the rated speed. Due to the large power loss, this method is expensive and less efficient compared to the field control method. So this is the comparison between the field control method and the armature control method.